Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over some weak acid, weak base equilibria practice problems. So here's problem number one. So you have a 1.00 molar HOAC concentration or solution. HOAC is just shorthand for acetic acid. Calculate the equilibrium concentrations for acetic acid, the H3O plus or H plus concentration, and the acetate ion that's left over, which is represented by OAC minus, and then calculate the pH of the Ka, or if the Ka is 1.8 times 10 to the negative 5. So we need to find the equilibrium concentration. So this is a weak acid, it's an equilibrium. We're going to have to do an ice table. So let's set up our ice table. So here we go. We have ICE. And with regard to water, water's liquid, so we're going to ignore the liquid. Anything in this column we're going to ignore. And so we're told we're starting off a 1.00 molar solution of the acetic acid. So we'll put initial here is going to be 1.00. And we're not given any information here, so we're assuming that we have zero product initially for this problem. Okay, so since we have zero product, then that means that the shift, I shouldn't say shift, but the change is going to be in this direction. So we're going to lose some of our reactant and we're going to form some of our product. So what amount is that? We don't know, so we're going to use X to indicate the amount. So here we're going to lose an X amount, and here we're going to gain an X amount. And again, we want to make sure we're doing our stoichiometric amounts. So the balanced equation gives us a 1:1:1 ratio. So here we have 1x plus 1x, 1x. Okay. And then for our equilibrium, we're just going to add these two together to get our equilibrium expression. So at equilibrium here, the concentration is going to be 1, 0, 0 minus x. Here it's going to be 0 plus x. It's just going to be whatever the concentration of our substance is going to be x. And here it's also going to be x. So now that we have our equilibrium expressions in terms of x, we can now plug that into our K expression for this. Since it's an acid with water, then it's going to be our Ka. So the Ka expression, so Ka is equal to the concentrations of these two raised to their powers of their coefficients. But those coefficients are 1, so it's just going to be H3O plus. So the concentration of H3O plus times the concentration of the acetate ion OAC minus. Oops. Sorry about that. Lights went out again. So here we go. So then that's going to be over the concentration of our acetic acid, which is going to be HOAC. So there's our equilibrium expression, our Ka expression. So now we just plug in these values for these. And so what we end up here is, so both of these are x, so it's going to be x squared, or we'll just do x times x. And so then this down here is going to be 1.00 minus x. So 1.00 minus x. So there's our Ka expression in terms of x. And so we can, now at this point, we can use the x is small approximation. We could double check that here. If we look at the Ka our equilibrium constant for this acid, and we compare that to the initial concentration. This is so much smaller than the original concentration that we can assume that X is going to be small. We'll have to use the 5% rule to check it for its validity, but this is more than 1,000-fold difference between 1 and 1.8 times 10 to the negative 5. So we'll go ahead and do that. So we'll get rid of X. We'll assume it's so small that subtracting it from 1 isn't going to change anything. So that means that this 1.8 times 10 to the negative 5, so we'll write that here. So 1.8 times 10 to the negative 5 is going to be equal to X squared over 1.00. So if we multiply both sides by 1, that doesn't do anything. So if we square root both sides, we get X. And in this case, if I look, X is equal to 4.2 times 10 to the negative 3. So there's our X. Now we have to use that to do our check, our 5% rule. So we're going to take our X, so 4.2 times 10 to the negative 3, divide that by the original, which is 1.00, and then this is molar. I should put molar down here, so that's molarity. This is molarity. Times, oops, I did times 100, and so that's going to give us 0.42%. So that is less than 5%. So our X is small approximation is valid. So we can go ahead and use that X for our other calculations. So now what we do is we take this X and we subtract it from 1. That'll give us the equilibrium concentration of the acetic acid. And then our concentration for H plus and OAC, the acetate ion, are equal to X. So the concentration is, let me double check my work here. So then 1.0, so this is going to be the acetate ion concentration. So this is going to be HOAC. Concentration is equal to 1.00 minus 4.2 times 10 to the negative 3 molar. And that's going to be equal to, let me calculate that. And that's going to be 0.9958 molar. And then the concentration of H plus, so the H3O plus concentration is going to be equal to the OAC minus concentration, and that's equal to X, which is 4.2 times 10 to the negative 3 molar. So those are the equilibrium concentrations of those substances. And so the next thing is to calculate the pH with this Ka. So the pH is based on the H plus concentration, which is right here. So all we need to do is take the negative log. So pH is equal to the negative log of this H plus concentration. So 4.2 times 10 to the negative 3. And so therefore pH is going to be equal to 2.37. And so one thing to remember about significant figures is that whenever you take the log of something, the number of decimal places that you have in your answer should be the same as the number of sig figs you have in the number that you are taking the log of. So here I have two significant figures, 4 and 2. So therefore, I should have 2 decimal places in my answer, and I do. So this is problem number 1. Let's go ahead and do problem number 2. Okay, here we are with problem number 2. So now we're dealing with a weak base here. So here we have 0.010 molar NH3 solution. This is ammonia. So ammonia is a weak base, and they're asking us to calculate the pH. And they gave us the Kb, which is 1.8 times 10 to the negative 5. And here we have the balanced equation. So remember, the Kb is associated with the base reacting with water to give us products. So again, we're going to want to set up an ice table so we can do our equilibrium, find our equilibrium expressions, and then put that into our Kb expression. So first, the ice table. So we're going to set up our ice table like so. And so our initial concentration of the base NH3 is 0.010. So we'll write that here. So 0.010. Now for water, since that's a liquid, that's not going to be part of our information. So we'll cross that out. And then we have here 0. Concentration. So we're starting with 0 for both of those. We're not given any information, so assume that it's 0. And then now we do the change. Since we got 0, we know it's going to go this way, so we're going to lose some of our base and we're going to gain some of the conjugate acid and some of the hydroxide. So it's a 1 to 1 to 1. So this is going to be minus x. This is going to be plus an x amount and plus an x amount. And now for the equilibrium, it's just adding the 2 rows together in each column. So this is going to be 0.010 minus x. This is going to be x, and this is going to be x. So now we have our equilibrium expressions in terms of x. Now we just write our equilibrium expression for Kb, the Kb expression. So here Kb is equal to the OH minus concentration multiplied by the NH4 plus concentration. And that's going to be all over the NH3 concentration. And so this is equal to the Kb, of course, is again equal to 1.8 times 10 to the negative 5. And now we can plug in our equilibrium concentration expressions in terms of x. So both of these are equal, so that's going to be x times x over, and then this is 0.010 minus x. 0.010 minus x. And so again, if we look here, our concentration, we're looking at our concentration that we started with and compare that with the Kb. And we'll notice it's about 1,000-fold difference. So we can go ahead and do the x is small approximation, but again, we have to always verify with the 5% rule. So we'll assume that x is small, so it's going to be negligible, so we can get rid of it. It's not going to make a difference. And so now we can solve for x. So we'll have 1.8 times 10 to the negative 5 is equal to x squared over 0.010. Now we just multiply both sides by 0.010, and then take the square root, and we'll get x. And then when we do that, we get x is equal to, what do I got? 4.2 times 10 to the negative 4. So now that I have x, I have to verify that my x was small, right? So here, now I'm going to do the 5% check. So do the 5% rule check. So I'm going to take the x value I got, 4.2 times 10 to the negative 4 molar. Forgot to put molar down there. And then divide that by 0.010 molar, multiply that by 100, and there I get, where's my check here? Hold on a second. And that's going to be 4.2%. So 4.2%, still less than 5%. So therefore, my x is small approximation is valid. So I can keep my x, and then I can take x and plug them into my expressions here. So then that means that the concentration of NH3, excuse me, is equal to 0.010 minus 4.2 times 10 to the negative 4. And that's going to be equal to 0.00958 molar. And then, of course, the NH4 plus and the OH minus are equal to each other. So that is, so the concentration of NH4 plus is equal to the concentration of OH minus, which is equal to X, 4.2 times 10 to the negative 4 molar. But it's asking us for the pH. So pH is the negative log of the H plus concentration, but we don't have the H plus concentration. We have OH minus concentration. So we're going to have to use the relationship between OH minus and H plus and the Kw. We know that Kw is equal to the H plus concentration multiplied by the OH minus concentration. Or, so let me write that down here. So Kw, which is equal to 1.0 times 10 to the negative 14, that's going to be equal to the H plus concentration multiplied by OH minus concentration. Or we could use the pH plus POH is equal to 14, right? Either one will work. So if I do this route, I can find the H plus concentration and then take the negative log of that. Or I can take the negative log of the OH minus concentration and then subtract that from 14. Either way works. So I'll do the POH. So POH is equal to the negative log of the OH concentration, which is 4.2 times 10 to the negative 4. And then that's going to be equal to 3.376. So 3.376. And then using pH is equal to 14 minus POH, then that means that the pH is going to be 10.62. So pH is going to be 10.62. Let me double check. And that is the answer. So that is the pH. And so that's two problems that I went over. So I did one for a weak acid, one for a weak base. So hopefully this was helpful. Hopefully this gives you some confidence in doing your own problems with weak acids and weak bases. If you enjoyed this video, if you learned a lot from it, then please, by all means, like the video, hit that like button, subscribe to my channel, make sure you hit that notification bell, and when you do, hit that all button so that way you can be notified by all the videos I put out. And then finally, share this with your friends and put a comment down below in the comment section. Let me know what you think. Ask me any questions. I'd love to hear from you. Thanks for joining me and have a great day.